So this is part 2 of structure in cross-linguistic phonetic realization. So in the last section, we ended on this slide where we observed covariation of talker mean VOT among stop place of articulation, and that's on the right-hand side. But what we also can take away from this covariation is the fact that the phonetic realization of these stop consonants cannot be wholly independent of one another. So there's something that's yoking the phonetic realization together. So in this part, we're going to explore that a little bit more and perhaps explain what might be going on with a uniformity constraint on phonetic realization. And then we'll be looking at covariation of mean VOT, not just across talkers, but also across languages. So what is this uniformity constraint? What we're positing is that within the phonetic grammar of an individual talker, the mapping from a phonological feature value to its corresponding phonetic targets should ideally be identical for all segments specified with that feature value. So what I'm hoping you noticed in the last slide was that the phonological surface segments, PT and K, well, they all share a distinctive feature, namely plus spread glottis. Ideally, the feature plus spread glottis is realized into a set of phonetic targets in the same way for PT and K, independent of the other features that are present in each of these feature matrices. Now, we have been looking at VOT, which reflects the phonetic targets corresponding to the shared plus spread glottis feature, but I want to emphasize that VOT is not the phonetic target per se. So it is not that a speaker is trying to make the VOT of PT and K uniform. It's that the phonetic targets giving rise to VOT should be uniform. I say this because it is well known that VOT does differ by place of articulation, which we'll get into a little bit more later, but the labial VOT tends to be shorter than the coronal VOT, which in turn is shorter than the dorsal VOT. So cross-linguistically, that is the tendency. So VOT is not the phonetic target, that is the observed acoustic output. But there should be a set of phonetic targets underlying VOT that is uniform. Now, the proposed phonetic targets here are the glottal spreading gesture, its duration, and its timing relative to the oral constriction. So the plus spread glottis feature, again, suggests there should be a glottal spreading gesture. The phonetic targets would then take that glottal spreading gesture and indicate how long it should be and how it should be timed relative to the oral constriction. Now, as long as there is uniformity in these phonetic targets, there should be covariation in VOT. I'm going to go into this a little bit more later, but covariation of VOT arises due to approximate underlying identity in the phonetic targets, despite the fact that there are slight differences in the observed VOT means. Remember, VOT is very surface, that is the acoustics, but there are abstract phonetic targets that might be articulatorily specified, at least in this case, that give rise to these strong correlations. So as a constraint on phonetic realization, uniformity should extend to other languages, other phonetic dimensions and segments, and also other populations. So we're going to be exploring some of these branches today. But overall, we want to ask, to what extent is uniformity a universal constraint on phonetic realization? So to start off with, we're going to take this case of VOT covariation in American English and extend this across languages. So previous research actually has identified pretty consistent relationships, at least in the VOT ranking, between place of articulation. So as I've said already a few times now, VOT tends to increase with more posterior places of articulation for a given speaker. So the VOT for P is less than that of T, and in turn less than that of K. So some previous research, some really foundational research on this comes from Cho and Latifoga in 1999. They investigated 18 languages from 12 different language families in a single corpus and looked at systematic relationships in VOT and also just variation in VOT. They did observe the well-known ordinal relationship for the most part. They also noticed consistency in the differences between place of articulation, noticing that, it seems to be that the difference between P and T tends to be about this much. This suggests that they also observed the presence of a linear relationship between stop categories, but they never explicitly tested it. So what we want to do is look at to what degree VOT might be structured across languages. And similar to Cho and Ladefoged, asked, do we observe the expected ordinal relationships? And importantly, do we observe strong linear relationships between stops within a laryngeal series, as we do for American English? Laryngeal series here just refers to a set of stops that differ in place of articulation, but have a shared voicing specification. And sort of taking Cho and Ladefoged one step further, we're going to be asking whether these VOT relationships emerge in a very large and diverse number of languages. So to do this, we conducted a meta-analysis of the literature. We are very fortunate with stop VOT because it happens to be one of the phonetic measurements that everyone and their brother measures. So there have been many studies on stop consonant voice onset time coming from a wide range of languages, populations, etc. So we simply combed articles, theses, grammars, and so forth for previously reported VOT means. So we did not actually touch any audio file. This was just collecting data from the literature. The criteria for inclusion in the present study was that the data had to come from adult native speakers of the language, and there needed to be at least 2 stops within a laryngeal series. So any language or any study that only reported one place of articulation wasn't included. Importantly, we also looked at the 3 clusters of VOT that have been documented in the literature. So in the American English study, we focused primarily on long lag VOT, which is the VOT example at the bottom here. Cross-linguistically, though, and actually even in American English, you might observe short lag VOT and also lead VOT. And they have different acoustic profiles. So we classified lead VOT as having an average VOT among the places of articulation less than or equal to 0 milliseconds. Short lag was defined as having an average VOT less than 35 milliseconds and above 0 milliseconds. And long lag VOT was classified as having an average VOT greater than or equal to 35 milliseconds. Lead VOT actually refers to the case where the onset of vocal fold vibration occurs during the stop closure and might also follow all the way up to its release. So you actually get a negative VOT because the onset of voicing precedes the stop release. And so you can see that here in the waveform. So the periodic part is the vowel. Short lag VOT has a stop release with a bit of frication at the release, but it tends not to have any additional laryngeal gestures like vocal fold vibration during the closure or aspiration after the release. And long lag VOT tends to correspond to a stop release that has a bit of frication and also an articulatory gesture of aspiration, which is some frication at the glottis. And this is what's characteristic of American English word initial stop consonants p, t, k. Short lag VOT and lead VOT are more likely for American English b, d, g. So short lag would be b, d, g, lead would be b, d, g. And so some languages actually make their voicing contrast between lead and short lag VOTs. It's actually not going to matter too much which cluster of VOT we're looking at because uniformity will apply regardless. And I'm going to walk through the mapping, so the phonetic realization from the phonological surface segment to some assumed phonetic targets for each of these 3 types of VOT, starting with long lag VOT, which is the familiar one from American English. So why do I say it's not going to matter for our analysis of uniformity? Well, it only matters that the stop consonants under investigation share some voicing feature. So in American English, we called that feature plus spread glottis, but we could have called it plus X, as long as that feature mapped to a set of phonetic targets that corresponded somehow to the laryngeal status and gave rise to and corresponded to the VOT values. So there only needs to be a shared voicing feature among the 3 consonants. For long lag VOT, though, we might consider a set of phonetic targets that corresponds to something like this. And specifically, it would be the duration of the vocal fold opening and its relative timing to the closure interval. So for long lag VOT, if we have a uniform duration of the vocal fold opening and a uniform relationship between, a uniform timing relationship between that vocal fold opening, or the glottal spreading, and the constriction, then we actually will observe slight differences in the place-specific VOT values, and we will also observe strong covariation among the VOT values in crosstalkers. Why is this the case? Well, it happens to do with physics. What you can see here is that the closure interval phases for each of the 3 places of articulation differ slightly. And this has to do with the fact that in order to delay the onset of voicing for the vowel, you have to build up the speaker has to build up the intraoral pressure inside the oral cavity, and that increased pressure relative to the subglottal pressure is actually what delays the onset of voicing. So that pressure buildup needs to be high enough so that there is time for a voiceless burst release and voiceless aspiration. Now, to build that pressure up, of course, we're working with different intraoral cavity volumes. So for P, the constriction is at the lips, and pressure needs to build up inside the whole oral cavity, meaning that it takes a bit more time to reach the necessary intraoral pressure. For T, the cavity is slightly smaller, and for K, the intraoral cavity is made behind the velum, and so it's between the glottis and the velum, and so it doesn't take that much time to build up the necessary pressure to delay the voicing. So this means that we get slight differences in the observed VOT because all we're observing is the burst and aspiration. So we are getting a shorter VOT for P than for T than for K. At least that's the expectation. Now, for short lag VOT, the story is basically the same. We have a shared voicing feature and uniform phonetic targets with this slight allowance for differences in the amount of time it takes to build up the intraoral pressure, but the duration of the vocal fold opening is the same. We've just removed the aspiration gesture here. And for lead VOT, instead of it being vocal fold opening, the uniform phonetic target might be something like the duration of vocal fold vibration and its timing relative to the constriction location and release. Okay, but again, the key part is shared voicing feature, uniform phonetic targets that here might be articulatorily specified, and they might in turn give rise to slightly different acoustic profiles in VOT. So our meta-analysis of the literature, we have over 1,700 data points coming from 36 language families and 147 language varieties. Again, we have data from long lag, short lag, and lead voicing. And listed here in the table are the language families, and in parentheses, the number of language varieties for each language family. So looking first at the range of cross-linguistic VOT variation, we have the histograms of VOT, language-specific VOT means. You can see the 3 clusters of VOT that I've referred to. So we have the lead VOT values, the short lag, and the long lag VOT, so nice trimodal distribution here. And what we observe is even within each of these VOT clusters is a wide range of variation, at least for the long lag and lead VOT values. Of course, the short lag VOT is by definition truncated in its variation. When we look at the relationships between phonological surface segments, we can also observe whether that canonical VOT order is sort of adhered to. So the uniformity hypothesis, at least with the current assumptions regarding the phonetic targets, does still predict that there should be an ordinal relationship of this sort. When we look across all VOT values, it is the case that in 95% of the cases, the labial VOT is shorter than the dorsal VOT, and in 91%, the coronal VOT is shorter than the dorsal VOT by some amount. A little bit more variation for the labial coronal ranking, and more variation actually emerges as we look within category, but it's still pretty high. So it's a fairly consistent ranking for the short lag stops, but there is some variation for stops especially with additional laryngeal complexity. So if you have aspiration or pre-voicing. Now, looking at the linear relationships between categories, I'm cheating somewhat here because we do have a trimodal distribution and I'm just looking at one correlation through that whole thing, but it is a beautiful correlation. They are almost perfectly correlated. So even if the ordinal ranking, or the ordinal relationship is slightly unexpected, the linear relationship is pretty much in line. with what we would expect given uniformity, that there should be minimal deviations in the phonetic targets for the shared laryngeal feature. If we break this up by VOT cluster, for long lag VOT, we are still observing strong and significant correlations. So a lot of variation across languages, but there seems to be a tight relationship between places of articulation. For short lag VOT, the strength of the correlations drops a little bit, but they are still significant. And for lead VOT, we get very strong correlations across languages between these places of articulation. So if you want to explore these correlations more, I have a Shiny app on my website that you can go to, and you can even highlight certain languages or language families. And there's also a link to the actual data in this data set in the lower left-hand corner of the website. The strong cross-linguistic structure in VOT does suggest an influence of uniformity in the phonetic realization of this voicing feature, or this feature X that maps onto some laryngeal phonetic targets. And the covariation that we observe arises from underlying identity in the phonetic targets. There are still some open questions. There are very few outliers overall with respect to the best fit line, but several languages have varied ordinal relationships, especially among the lead and long lag VOT series. So do we have the targets wrong, or does the language actually violate uniformity to some degree? And then another big question we'll be exploring today is structured variation of this type specific to VOT, or do we observe it for other phonetic dimensions? So next we'll be turning to sibilants, and specifically their places of articulation.